question about gravity. Okay.
Hey guys!
Hi, Dinka.
What are you doing in here?
We're just having conversation. Sit down.
Okay, please. What will happen if I jump in there? You will fall, of course. What? Because something called gravity. What is gravity?
Gravity is something that every time you jump, you will experience gravity. It pushes you back down to the ground. And without gravity, you will float into the atmosphere and along with all of the other matter in the earth.
How does it work?
Gravity is the force that attracts the body of the center of the earth and or toward any other physical body having mass, of course. And because of gravity, if you drop something, it will down instead up, and something like that. I will tell you a story about Isaac Newton.
Great discovery to Sir Isaac Newton, who was born in England the same year that Galileo died. Legend has it that Newton was relaxing in an orchard one day when he saw an apple fall from a tree. This simple incident caused him to wonder why the apple had fallen to earth while the pale August moon continued to sail contentedly overhead. It was a eureka moment of insight for the young man. He realized that the same gravitational force acted on the apple and moon alike.
Yes, and you see that? It's a kite, and the kite is falling down to the ground. It's because gravity. And I have some experiments that will prove about gravity.
In 1905, Einstein published his theory of special relativity, which explored the link between space and time.
In Einstein's view, there isn't really a separate thing. There's space and then there's time. But there's just one thing, space-time, that we all live in.
He thought of this new space-time as a fabric weaving together space and time. In 1915, Einstein developed his theory of general relativity, which modified special relativity to include gravity and its effects on this fabric of space-time.
Welcome to the bouncy trampoline of gravity. We've taken our fabric of space-time, stretched it taut, and placed a heavy weight on it. See how it warps the fabric of space-time. When we roll the ball across the fabric, it magically seems to be drawn or attracted to the massive weight at the center.
General theory of relativity was a new theory of gravity, one that told us that gravity worked because space and time were curved in the presence of matter and could respond dynamically. Space itself could expand and contract in the presence of matter. A crazy but true idea.
Mass is a term used to describe the energy and matter that objects contain. The larger the mass of an object, the greater its distortion of the space-time fabric. The stronger the effects of gravity.
Gravity is not really a force. It's a fabric. It's a shape of space and time. And we just move along the curves of these shapes. And the act of doing so takes what would otherwise be a straight line to you and bends it into what you now describe as orbits, as trajectories, as pathways through the cosmos.
Einstein said not even light can escape the effects of gravity. As crazy as this sounds, proof conveniently arrived in 1919 in the form of an astronomically large experiment based on a solar eclipse.
General relativity said that if you look at a star on a path of light that goes right past the sun, you would see it shift just a little bit because of the gravity of the sun. So Arthur Eddington actually went out to test that theory during the solar eclipse of 1919 and actually photographed stars when the sun was blocked by the moon and you could see the stars behind it.
The ability to see objects that were actually behind the sun proved that objects could warp space-time. Einstein became a superstar overnight. He received the Nobel Prize in Physics in 1921. But general relativity opened a Pandora's box for Einstein.
Small rock. You couldn't do it just by wishing the rock would move. And you couldn't do it by magic. And you couldn't do it by ordering the rock to move. There's only one way you could make the rock move, and that's by making a force act on it. What's a force? That's something that pushes or pulls something else, like the force from a hand pushing the rock or pulling it. It doesn't matter what does the pushing or pulling. As long as it applies a large enough force, it can move the rock. In fact, the rock can even be moved by a force that you can't see, if you do this, for instance. When you do that, the force moving the rock is called gravity. Gravity is a force pulling the rock toward the center of the Earth. Gravity pulls everything else in the world toward the center of the Earth also, including you. Gravity was pulling on the rock all along, of course, but when the table was there, that kept the rock from moving down. If you remove the table, you allow the force of gravity to move the rock. And when you pick the rock up again, you use another force, this time to lift it. So whenever you make this rock move, you do it by making a force act on it. In fact,
to understand why the moon is so important to the Earth and to the exploration of space, let's consider a new way to view the solar system. We'll turn the solar system on its side and imagine that it is a giant tabletop. Objects on the tabletop are in free space, and it takes very little energy to move around once there. Wells in that table show the energy needed to get into space from the sun, the planets, and other bodies. The more massive the object, the deeper the well. It takes enormous amounts of energy to climb up out of the deep planetary gravity wells to get to the plateau of free space. But although we Earthlings are gravitationally disadvantaged at the bottom of the deepest planetary gravity well in the inner solar system, we live right next to a more practical source of space materials, the moon. In contrast to the Earth's deep gravity well, the moon sits in a gravity dimple. If the Earth's gravity well is 22 steps deep, the moon's gravity dimple is only one small step deep. Most of the cost and danger of spaceflight comes from the difficulty of crawling up out of the Earth's deep gravity well. Instead of using Earth materials for construction in space, we can build space stations, power satellites, or spaceships using raw materials launched over the curve of the moon's gravity dimple and let these lunar materials roll downhill to high orbit around the Earth.